All right. So welcome back to class. Today is session 8 and will be the last day of our class. So on this very last day, I'd like to um well instead of introducing uh let's say new content, I'd rather spend for us to spend some time on the going through working through a few problems regarding algorithms and especially competitive uh, especially problems that have uh, occurred in contests or competitions. And I believe that would be a more, I guess, useful uh, use of the time, more efficient use of the time. So that being said, just a quick review on what we did last week. So the very last week, oh, sorry, not last week, just a few days ago, we looked at uh, the algorithm, what's called greedy algorithms. So if you remember, greedy algorithms are when you're trying to choose the best case scenario for for uh every time, and that would also turn out to be the best result for the entire solution. With that, we did went over quite a few problems, but we never really got to code any of them. Uh, So I believe one of the optional homework was to work through the assignments that you work through one of these problems. And don't worry if you haven't, that's all right, because in class we'll be going over a few of them actually. Right, that being said, let's take a look at the first problem. Um, so one thing I'd like to point out beforehand is that all questions that we'll be doing today are going to come from USICO, which is the USA Computing Olympiad. It's a computer science, well, it's a competitive programming competition, and that has a strong focus on algorithms. They have 4 divisions: bronze, silver, bronze, silver, gold, and platinum. And for the case of this course, we'll only be looking at questions from bronze and maybe some of the silver divisions. That being said, here is the first question. I'll zoom in a little bit. All right. Give me a second. Okay. So here's a problem. I'll read it. Basically, uh, well, Farmer John's cousin Ben happens to be a mad scientist. Okay, well, so for every question from the USCOs, from like USCO, you would have a a description. It's gonna give you like a quote unquote real life situation or some sort of situation for you to try to solve. And when you and then something well, yeah. Then it's going to give a bit specifications. It's going to tell you how the data is going to be inputted, or how it's going to be, what the input is going to look like, and then it's going to give you what should the output be. We can ignore the file and stuff because it's kind of changed, uh, and no longer the case anymore. I'll talk about a bit more later. Then they give you an output format, and then they give you give you one sample input. And then yeah, they give you a sample output and then give you I guess they give you a analysis. So I believe I got cut out. So before that happened, I was talking about how there will be a analysis on the why the output is. There will be a few more test cases when you could what have when what you could do is if you oh, give me a sec. Okay, yeah. Sorry. I just had to log into my account first. That there we go. So over here, if you log in, what you would do is you go to overview. Uh, normally it would be normally it would be like this, and then you would register for a new account, and then put in your stuff, and then log into it. Right. Uh, then let me log in real quickly. Then you'll be at this page. Uh, the problem that we're gonna go to here is over here. So after, now you see there's a little thing on the bottom where it tells you the language that you could choose and then the source file. So the Java code that you're going to be writing and you're going to be putting in. That being said, I'll put this question in chat in case you want to read along or read it on your own screen. With that being said, here's the question or the problem we're trying to solve. Farmer John's cousin Ben happens to be a mad scientist. Normally, this creates a good bit of friction at family gatherings, but it can occasionally be helpful when Farmer John finds him facing mixed and unusual problems with his cows. One thing is that Yuzuko loves Farmer John and their cows, so we'll just live with it. Farmer John is currently facing a unique and unusual problem with his cows. He recently ordered N cows. You see here is the specifications. N is within 1 and 1,000, consisting of two different breeds, H and G. He specified the cows in his order in terms of a string of N characters, each either H or G. Unfortunately, when the cows arrived at his farm and he lined them up, their breeds formed a different string from the original string. So essentially, you have two sets of strings. One is what it should have been, and the other one is what it is now. So they both are going to be a series of H's and G's. So let us call these two strings A and B, where A is a string of breed identifiers John originally wanted, and B is a string he says his cows arrive. Rather than simply checking if rearranging the cow in B is sufficient to obtain A, Farmer John asks his cousin Ben to help him solve the problem with his scientific ingenuity. After several months of work, Ben creates a remarkable machine, the multi-cow breeder Flipinator 3000, and this is capable of taking any substring of cows and toggling their breeds. All H's become G's, and all G's become H's in the substring. So Farmer John wants to figure out the minimum number of times he needs to apply this machine to transform his current order in B into his original desired order in A. Sadly, Ben's math scientist skills don't extend beyond creating ingenious devices, so to help Farmer John solve this computational conundrum. Okay, so let's look at the input format. The first line contains N, which is a number of cows going to be in the list or in the breed, or I mean in the string, or the number of characters in the string. Either way it works. The next two lines contain string A and B. Each one has N characters that are either H or G. All right, so here is their sample input, and let's take a look at it. This one is called, what is it called? Yeah, scientist. All right, this is what we got. All right, so here is the desired order, and this is the current order. What you want to do is have this order become this by flipping a certain series of letters or characters. Okay, so how can we do it? So, well, of course, we have let's just a few steps, I guess, in solving any kind of problem is first you'll be doing it by hand. You want to see how you could intuitively approach this kind of problem. So here we are. The first try would definitely be flipping this because H doesn't match with G, so I got to flip it somewhere over here. All right, but where should I end? All right, so probably right here, just because then I don't have to flip this again, but there should be multiple ways. Let's see what they say. All right, so they said that you should probably flip the first one first. So GH. Then you would need to flip third and fourth, it will be G H H H G H H. There we go. So that's two steps. Or we could do something like let's see, another possible solution. All right, we could probably flip this entire thing. Yeah, we could do G G H H G H H. So that we flip this this. Apologies for the reconnection. Right. So in this solution, we flipped G alone, and then we flipped HH alone. Right. Okay. In this case, we flipped GGHH. Or we flip this part first, and then we could how can we flip this? Yeah, so we just flip this back. H H H G H H. Yeah. So still two steps, just quite a different approach, I guess. Okay. So now I'm gonna give you about 5 minutes to think about this yourself. See, maybe try a few other methods and maybe give it a try on, I guess, coming up with some sort of pattern. Like why what is some sort of rules that I can follow like in my mind or like by hand to solve this. And then we could like then use that to figure out what algorithms we're going to use or like what kind of uh code are we going to write. So I'm going to give you 5 minutes. Come back. So yeah, so about 23, I guess, is when you come back. And by then I'll explain how I would approach this problem. As always, if you have any questions, feel free to ask. I'll be available. All right, so it's about time. And now you might, some of you might have guessed it, that since that we are already talking about, I guess, greedy algorithms, this one has to do with greedy. And it might not come to you very intuitively, but or well, I guess greedy is intuitive, but I guess when you think about it, here is how I thought of this problem when I started. So imagine I would be scanning through these two from left to right. Okay. And then um whenever I see that there is a mismatch between the two strings, I know I have to flip it somehow, right? So that's when I will start flipping it. Now, when would I end? Well, I would end as soon as there is uh, a corresponding one. So if there's an H and an H over here, they should they correspond. Then I'm gonna stop flipping right here and only flip the ones that before it, which in this case is only one. However, in this case, I'll start flipping here because they mismatched, and then stop flipping right here because they matched again. Therefore, I'm going to flip these, right? And then that turns out to be actually the best solution possible. Two moves. Now you can try more of these, but due to the limitation of time, I would not be going into more specific, more examples. But now, if you try to, I guess, logic your way out of it, well, I guess logic your way through it, you can think of it this way. So, well, I don't suppose explaining why we should begin with it is necessary, but I would like to talk about why we should end as soon as there's a match. So, if we flip any matching cows, we would have to flip the cow back right away, which means that it's going to add an extra move, or at least it's not going to be any more efficient by including a already matching cow. Therefore, it's like we have, so we could have just skipped that part and start the next place. So it's never going to be more efficient if we like decides to flip some of the existing cows, right? So now that gives a really simple solution or code to write, because all you have to do is to count how many, I guess, intervals of mismatching cows there are, and that just requires one simple, I guess, iteration through the entire string. Uh, and there you go. You just have to count how many times a mismatch range interval. More specifically, instead of counting how many intervals, we just have to count how many start of an interval there are on a existing string on that existing string, and then that would be our simplest or most efficient solution, right? Because essentially, what they're asking for is the let's see, the minimum number of times the machine needs to be applied to transform B into A. We don't need to know how to do it. We just have to, I guess, print out the numbers. So that saves even more space. All right, so now let's try to code this. I'm going to copy this. There we go. I'll worry about this later. Of course, it could be resolved at the very end. Class. That's that's all right. Here is I'm not going to explain too much about this. It's just standard practice. How you would be reading through this, reading this in, but um, yeah. this is how Yusuko wishes you to input the file and output the file. So we don't have to worry too much about it. I believe, in fact, um, we could skip it by using terminal inputs. But give me a second. Let me see if I could find a working sample of it. Okay, yeah, we could just use scanner. It's not going to be too much more inefficient. Um, Scanner in equals scanner. And then we could system dot it. Right. Unfortunately, I'll have to import these again. Quickly resolve this. Or all right. So this line is simply trying to get a user input from you, right? So not much something that we really haven't touched on. Then we need n, integer n, which is the size of it, equals n dot next. Wait, next line. There we go. Yeah. Of course, we need to parse it. So integer dot parse int. There we go. So now we have the size, right, of the cow over here. We get the 7. We are now importing the 7. So okay, so now we need a array of char, and then that would be integer dot next line, right? And then we need to convert that to a char array because sorry, not integer. I'm saying in the next line dot to char array. This converts the input of this into an array, so it's for easier processings. And same thing to be done for B, which is the current set of cows that we need to operate on, I guess. To char array. There we go. Okay, so int. Now we need to measure how many, I guess, flips or like how many beginnings of an interval there are. So let's do int intervals equals 0. And then we need a loop, right? We can have a simpler way. It's like, so we have a Boolean called mismatched. False. I can't spell Boolean apparently. That's okay. And then while now we're going to loop through the entire array, right? So while let's find out for I dot a dot length or b dot length doesn't matter. They're the same size anyways. So do n actually more straightforward. Then if a I it's not the same as BI. That means like we have now found a mismatch. Then if it's already mismatched, if yeah, if yeah, we'll talk about this later. Mismatch, check mismatch. However, over here we need another statements checking if. Well, no, we don't need another statement, but rather, so that means it's no longer mismatched. So we need to change mismatch to false again. Right. Yeah. So over here, I need to check if it's mismatched because it might be like within in the middle of a what is it? What do I call it? It might be in the middle of a interval of mismatched characters. So like it might be the second character, it's not gonna be the same, but but since it's already mismatched, we aren't gonna add another interval to it. So therefore, this condition checks if the basically this condition would only pass if the letter previous to this mismatched letter is the same. So if it is, that means like this is the first mismatched character of this interval. Therefore, mismatched equals true. So this is what I call this is what it's called a flag. It's being like triggered. Then we have intervals plus plus. You could also name this answer. It really doesn't matter. Yeah. Then now we're done of the entire code actually. System.out.print, and then we could just print out the intervals. Or num interval might be a better name symbol. Interesting. Reflector. Okay, well, that's fine. Just do it the harder way. That's actually it for the code. But they want you to close it, it doesn't really matter. Uh, not in the context of this code. Okay, I'll rename this, I guess. Inner, just trying to follow good naming habits. All right, that's it for the code. We can run this and see if it works. There we go. Run it. Okay. Uh, where did that come from? Oh, it's gotta be the comments, isn't it? It's rather frustrating. There we go. Don't know what's wrong with it. Oh, okay. Java C. Paste it in, enter. It gives us number 2. All right, so that's actually it to this question. Of course, we could also get a few more test datas. We could skip it. I don't want to download it. But in case you wish to, you could go try it yourself. So code is not very hard. All we did is going through the for loop, check if it's mismatched. If it's not, well, checking for the beginning of some sort of interval. And then we print out the total number of intervals we found. Cool. Uh, that's it. And we'll move on to our next question. Cool. Let me see which one's next. Mm. Right, so let's work on I guess, a problem that's not so much related to, um, what do you call it? Let's see. Trying to find a one that would be rather good to talk about. Okay, this one do. All right, so here is the question. All right. Farmer John's three prize cows, Bessie, B, E, and M, are always wandering off to the far reaches of the farm. He needs your help herding them back together. The main field in the farm is long and skinny. We can think of it as a number line on which a cow can occupy any integer location, and the three cows are currently situated at different integer locations. Farmer John wants to move them so they occupy three consecutive locations, six like numbers like 6, 7, 8. Unfortunately, the cows are rather sleepy, and John has a hard time getting their attention to make them move. At any point in the time, he can only make a cow move if she's at an endpoint, either the minimum or the maximum position among all cows. When he moves a cow, he can instruct her to move to any unoccupied integer location, as long as in this new location, she's no longer an endpoint. Like you can only move one cow into the middle of two cows. Observe that over time, these types of moves tend to push the cows closer and closer together. Please determine the minimum and maximum number of moves possible before a cow becomes grouped in three consecutive locations. All right, so here is the input format. It's going to be a line with three space separated integers, given location of S, B, E, and M. Each location is an integer in the range of 1 to 10 to the 9th. So when you see the number 10 to the 9th, you immediately know that you cannot brute force it. What I mean by brute force is try every single possible combination to get this result, to get an answer. Because 10 to the 9 would run out of efficiency. So like it would not, Yusuko has a limited amount of time and space for a problem to run. And you have to fit within the time given and the space given. So an indicator is 10 to the 9. As soon as some number reaches this, it's rather hard to brute force, or you can't brute force it. So the first line of output should contain the minimum number of moves. Second line should contain the maximum number of lines of moves. All right, so let's take a look at the sample input. What do you call it? Oh, what's it called? CP cow herding. Herding dot cow. CP cow herding. The link, and then we have the test data. All right, let's separate this out onto I guess, a number line. 1, 2. There we go. So we have B, E, M, indicating the cows. Right. So what they have offered is the first move, well, the minimum number of moves is 1. So you move from 46, 48. Let's see. Yeah, because 8's right over here. It's in the middle of the two numbers. Therefore, you just move B to where 8 is, and you're done. Minimum is 1 step. B 4 to 8. Okay, 1 step. Okay, now let's look at max. Is 2 moves, because you can only move a cow within into between two cows. So if you move 9, it can be moved to 6, then 7 can be moved to 5. So this one can be moved to 6. This one can be moved to 5. Now, what if we do something else? You could always try some other combinations, but there isn't really many options you could try. You can only either move B or move M. Got two, actually. Yeah, so two options. You can move M to like where 5 is, then B to 6, or you can move M to 6 and then E to 5. Either way works. I'm gonna just do M 9 to 6, and then E 7 to 5. There we go. And that's two moves. All right. So now that's one test case scenario. And let's see how this is processed. All right. Let's think of it more generally. So suppose there are three counts, like where B, E, M are their numbers, or A, B, C, X, Y, Z, whatever you call. I'm going to call them A, B, C just because they are easier to think about. So A would, so we start out with three numbers, right? A is less than B, less than C. And then there are, now let's look at different cases. So like if we want to talk about the minimum number of moves, well, there are a few cases. One, if they are already consecutive. So have supposedly numbers A, B, and C. A, B, C are right next to each other, then 0 moves. You're done. Then if there is like a one gap, there's like one gap between them. So let's say like A, B, then empty spot C, then it's one step. Same thing goes for A, B, A space B, C, whatever. Or like 17, 21, 23. Yeah. And then for any other cases, it would always be two moves. Other cases, two moves. How so? So if there is a gap between A and B, and then another gap between B and C. So let's see, A, B, C. Okay. What you would do is, well, we could either do like move A to between B and C, or C to between B and A. Or we have something like A, B, space, C. Then we just, all we're gonna do is move A to this spot, and then B to this spot. And then, of course, any other numbers, yeah, all the other numbers are going to work as well. Let's see. Let's have an example with 3 spaces, A, B, C, right? So all we would do here is move A to over here, C to over here, or anything. Yeah, literally. For anything that's longer, even B, C. Right, we would always move A to B plus 2, so leave a spot in the middle. And now we're into this case, and it requires another move. So as you can see, it's a progression of cases. You have this very worst case, I guess, or the outer case, case 1. You have what? This is called case 3, I suppose. You have case 3, and then you can always transform it into case 2 by one step. Right. So case 3 is case 2 plus 1. Move. Case 2 is actually just case 1 plus 1 move. Sorry, this is case 1. Case 2 is case 1 plus 1 move. I mean, or of course, it could be like, yeah, so the maximum move is 2. And well, there you have it. Here is simple as that. So now we know how to approach this. That is to always move it to b plus 2 and then move the action number into the middle. We just have to follow that every time. All right. So that's the min case. Now let's look at the, I guess, max case. So for the maximum number of moves, you're trying to see this. So if you have a gap between well, there's going to be a gap between A and B, and then a gap between B and C, let's say. A some sort of gap, B some sort of gap. So whatever you do, as soon as you move a space, well, as soon as you move one of those cows, one of those spaces will definitely go away. So like there cannot be any cows within this gap. Or if you're moving this, it's not gonna be in that gap. So what we have to do is we will be moving the cows so that the other gap has like every empty space used by a cow at some point at time. So what it means is we have to ensure we always have two adjacent cows at some sort of endpoint, so we can have more available space or like more available turns. So what it looks like is essentially you're swapping A and like, let's say C is fixed. What we are essentially doing is swapping B and C and B and C until there is no more spot. And we will always be like, let's say we have A, B, and a lot of space, and C, right? Our first step would always be move move B over here. We'll move A over here. And so we could keep all the space over here where we can again flip it again, and then you see where I'm going with this? You could always B and then A, and then you can have 2 more spots, right? This is how it's going to take the longest. And then, well, and lastly, we have another case to consider. That is, what if both has spaces in between, right? So let's say B, uh, let's put it here. All right, so which one do we move? Well, in order to ensure that there's the longest gap between this, so we can have more steps, we're always going to move the one with the smallest gap. So in this case, it's going to be like this, right? And then I'm not going to continue much more than this, but see, and you might be able to tell the pattern again. I'm just repeating the same thing I've done over here, but in a different order, right? Okay. So that's it. Yeah. Okay. Now let's try to code this. Public class, public CP cow burden. I'm gonna copy this basic structure over here. Let's make life easier. Gonna have this or that. There we go. We're gonna get rid of all this. So, essentially what we want is the scanner. Right. Then we're gonna read in A, B, and C individually. A equals in dot next int. Int B equals in dot next int. Int C equals in dot next int. There we go. All right. So now I guess well, before we do anything, we need to, I guess, arrange it somehow, right? So because we all of these are built on A is less than B is less than C, we need to order these the way that it's going to work, right? So if you remember how you would arrange stuff, you will have an int temp, and then we could check, we could write actually, just write a little function, helper method over here, public static, and right, we can't, okay, here. We'll move this into int A, int B, int C. So that case, we could manipulate this within the other function. Of course, these will be removed. Temp no longer exist. Static. And then public static swap int x, y, just so we don't mess them up. Int temp equals sorry, trying to think. Honestly, ignore what I said. This gets a little messy and annoying and unnecessary. Just we could just, because this is more or less just trying to get stuff working. We could do this. If A is larger than B, then we could swap them, right? Trying to be a little lazy here. Int temp was A, B, A equals B, B equals temp. There we go. It's this simple swap method. What? Move this uses assignment to local variable. Okay, that's fine. We'll take care of it later. Else if, okay, well, so, if doesn't exist. Else if, let's see what else. B is larger than, no, not else if it's larger than C, then we need to do this all over again with C. B, B, C, C. Okay. Lastly, we need to check if A is, well, we need to swap it again, because if A and C are swapped, if A and B are swapped, then B and C are swapped, then we have to swap A and B over again. So just copy this over here. Code is a little rather messy, but it's easier this way. All right, so we just now check if C equals A plus 2. Then we can just print out 0. Because we know that A, B, and C must be in this particular order. A, something, B, and then C. If A is literally just 2 spots, if C is literally just 2 spots away from A, you know that B is within it, and there you have it. This is the minimum number of steps. Nothing else is needed. Nothing else is more. Right. So now we have else if B equals A plus 2, or let's say like C equals B plus 2, right? Because these are essentially the same case, just a little different. Oh, so yeah, sorry. Should I mention this? What I'm doing right here is trying to figure out the minimum case, right? Because through the analysis over here, we have like 2 cases. Oh, 3 cases, 0, 1, or 2. So right now, right then I just finished processing the first case. Now I'm trying to process the second case. Out 2. If you really want to, we can remove these. But yeah. no, sorry, 1, because ooh, what's going on? This is a plus 2c plus. Yeah, so this is the case where like B has there's a space between B and C, no space between or if there's a space between and like that, or like that, right? Either way is one step. So now that and identity is gone. Lastly, we're left with all the other cases where it's just simply 2. Now we have the minimum step figured out. We could do the maximum step. So the maximum step is actually rather simple because right here, think about how this works. For this case, let's just finish this case so we could know what the numbers are exactly. C, R, B, C. There we go. We're done. Right. So we moved a total of once, twice, thrice, 4 times, 5 times. Right. So 5 times. Where did that number come from? It's actually just 1, 2, 3, 1, 2, 3, 4, 5, 5 spots in between. So which is let's assume 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's 8 minus 2 minus 1. So what we have here is C minus B minus 1. Right, because C minus B gives you 6, and the number is 5, 1, 2, 3, 4, 5. So we have to get rid of one of the AND cases. So it's C minus B minus 1. Or it could, in this case, it would instead be B minus A minus 1, because right here, this is the part that we're focusing on. So we're trying to find the minimum of the maximum of one of those numbers. And that will be our max case. So all we do is print out the max of B minus A or C minus B, and then subtract 1 from that. And of course, you could just, well, C minus B. You could put minus 1 in the max part, but I prefer it here because it's a little easier. Integer dot max probably. There we go. And actually, that's it. That's all of our. That's what there is to this question. We can run this. See how it goes. 749 gives us 1 and 2. In fact, that is the solution, 1 and 2. Of course, you're more than welcome to try any other solutions. But that being said, yeah, this one's a fairly simple solution. It's a little hard to wrap your brain around it, especially how seemingly complicated cases, situations have a very simple, I guess, pattern behind it. That which is what this part is doing. This, yeah. That being said, we'll move on to our last question since we have a bit more time. Try and let me see. I don't want to find a terribly hard question because all right, let's take a look at sleepy cow sorting. Here we go. Sleepy cow sorting from 2019. All right, so Farmer John is attempting to sort his N cows. Notice that it's 1 less than N less than 100. Conveniently numbered 1 through N before they head out to pastures for breakfast. Currently, the cows are standing in a line in the order of 1 through N, and John is standing in front of cow 1. He wants to reorder the cows, so they're in the order 1, 2, 3, with cows 1 next to Farmer John. The cows are a little bit sleepy today. So at any point, the cow can only pay attention to Farmer John's is the cow that's facing Farmer John. Right. Yeah. So sorry. forgot to mention that this doesn't come in the order of like 1, 2, 3. This is like 3, 1, 7, 6, 4, 2. Right? The cows are currently on order, and Farmer John is trying to force this cow, trying to change this configuration into this. Right. But there's some limitations. So only the cow that's paying attention, only the cow that's in front of Farmer John can understand or can pay attention to the instructions. So in one time step, he can instruct this cow to move K paces down the line. So he can at one with like one period of time, he can move the cow to any place down the line. And for any K in the range of like 1 to n minus 1, right? The K cows whom she passes will amble forward, making room for her to insert herself in the line after them. So essentially, Farmer John can only move the first cow into any positions in the line. All right, and now this one they actually gave a bit of a, I guess, a demo. So for example, suppose that n equals 4 and the cows starting off the following order, 4, 3, 2, 1. The cows can only pay attention to Farmer John is 4. And then if it's instructed to move 2 paces down the line, the order will look like this, right? Because 4 moves 2, moves behind 3, behind 2, now is 4 is out where this is. Now the only cow that can pay attention to Farmer John is 3. So he can only give cow 3 instructions and then to give to cow 2, stuff like that. And then he is trying to find the minimum number of steps required to sort the cows. They give you a number n, telling you how many cows there are, and then the n space cows in some sort of configuration. And then lastly, you output these steps needed. All right. Now let's look at this. Which one is this called? CP cow sorting. Yeah. Yeah. Here is our numbers. Let's look at their analysis. Okay, well, they don't have an analysis. That's good. So let's see how we can move this, right? We have to move 1 somewhere, and supposedly that would be after 4. So we could go to 2, 4, 1, 3, and then we could do 4, 1, 2, 3, and then lastly 1, 2, 3, 4. Right? That's how their, I guess, their solution is. So now let's make a little assumption. Assume that like, let's say it needs K moves to sort the entire row, to sort all cows. Right. So only the first K cows would change positions. So that means the last, I guess, n minus K cows do not move positions. That means they are already sorted in an increasing order, or else, like you can't move in any other way. To prove that, let's do like a few more examples, right? Let's say we have 4 cows, 1, 4, 2, 3. Okay. How can we sort this? Well, you will move 1 to behind 4. So it's gonna be 4, 1, 2, 3. And lastly, you move 1, 2, 3, 4. Maybe let's do like 4. Let's do like 4, 4, 2, 3, 1. All right. So we would move 4 to the very end. It would be 2, 3, 1, 4. Then we move 2 to where right after 1. So it's going to be 3, 1, 2, 4. Lastly, we move 3 into its position, 1, 2, 3, 4. Okay, well, there we have it. So that's 4 steps. This is only 3 steps, 3 steps. Now notice the pattern. So for the n moves that we did, for the k moves that we did, we would only do the number of moves that is necessary to sort the unsorted part. Because the latter part over here, you might be able to, yeah, this one. Actually, let's do another example. Or it could be for 1, 2, 3. Okay, what's the step required? 1 step. Why? 3 of these are sorted in their relative order already. Or in this case, 2 of them, or 1 of them is sorted in their relative order. And you only have to move the cows that are in front of this relatively sorted order into its positions. Now that might sound pretty familiar, doesn't it? That in itself is as like an insertion sort. Remember how that works? You have a relatively sorted portion, and then you're inserting the unsorted portion into the sorted portion. Right. So yeah. Okay, let's suppose like k is 0. What does that mean? That means n minus k, in this case, 4 cows are sorted already. So if k is 0, that means the cows are already completely sorted. If k is larger than 0, that means like the first cow can be inserted into the relatively sorted portion, which is n minus k. And then the last n minus k plus 1 cows are in original order. So like you just add 1 to the sorted section, right? So after doing that, k times everything's in sorted order. And yeah, because there are only n cows after k instructions, the cows are sorted. Therefore, all we need to do is to find the longest sorted suffix, or like the part that's towards the very end. So like we just need to find whatever the end has the longest like sorted kind of sorted list of array integers. Then we know what the solution is. Simply put, all we need to do is, you see 3, 2, 1. That means this is an increasing interval, right? We're trying to find how long this interval is, and then we will get the answer right away. And okay, so in this case, it's 3. Therefore, it's 4 minus 3 is 1. In this case, it's 1. Therefore, 4 minus 1 is 3. It takes 3 steps. This one is 2. 4 minus 2 is 2. 2 steps. This one is 2. 2 steps. See what I mean? All right. So now let's, well, since I already mentioned it, you can try writing this code yourself, I guess. The code is, I guess, rather simple. It doesn't require too much thinking. Well, sorry, that's the wrong way to put it. It's quite straightforward. 1 function is probably enough. So feel free to try it yourself. I'll put up the, I guess, like how the template should look like. Import java.util.scanner. Public algorithm. SEM. Scanner in equals use system document. All right, so that would be it. That would be your template, and fill out the rest, I suppose. I don't know why it's still in an error. Oh, I spelled it wrong. Oh, sorry. Yeah, so I'll give you about 10 minutes, and yeah, I'll give you about 10 minutes, and we'll come back at 23, which is when I will write my own version and show you my approach. As always, I'll be available to chat if you have any questions. Yeah, if not, I'll see you then.
喂喂，现在呢？太好了，唉，这一个周末过下来，我发现今天我一看票好少，好干净啊！唉，
Could you please mute yourself? Thank you. All right, so let's go over the solution. It's quite simple. Um, we have, let's see. Hmm. Right, so first we'll be getting in all the numbers. These n equals in dot next line dot integer dot parse. Right, yeah. And now we have for the whole loop that basically um, we need an array, right? So the array could be just R, I guess, or cows, whatever you want to call it. Cows. And so now cows equals. I guess we could just do this. N dot next line dot to int. Okay. Um. Let's see. I'm trying to see if there's a quick way. Nope. Okay, that's fine. So just do it by hand. Int. So int y equals int I, and cows I equals dot next. Voila. Okay, so everything's read in. Have int and this equals m-1 because that's the most max number of steps we're going to need. Then we're going to loop through everything. So for I equals minus 2, I is zero, I minus, because remember, that's one thing I didn't really mention is that you have to go backwards to like, it's easier to go backwards to get the entire list because usually that would take a bit less time. So now we check if cows, I is cows. If it is, then n equals I. Else, that means that we should reach the end. We just break out of it. And that's it, actually. Just do out. Answer. Missing the semicolon. That's all right. Okay. I'm not gonna close it. It's fine. All right. What are the test cases? Okay. See. 3. Just as we expected. From the over here. All right. So this is well end of this class and actually end of our class in general. Just a quick recap on everything done. Okay, it's gonna be too long, so I'm gonna skip that actually. I got 3 minutes. So yeah, I just like to talk a bit about where you could go next after this class. So something that you could definitely try, which something that you could and should definitely try is Usico. Usico is just for like practice and stuff. Just for like practice and getting better hang of algorithms, Usico is not a bad place to go. But of course, there are many other options such as Codeforce, LeetCode. Let me mention a few of those. LeetCode, Codeforce courses. These are all great places for you to practice your computer science skills. And each of them have fairly similar, I guess, range of questions and algorithms for you to study. They range from the easy ones, like the weak ones we have talked about so far, to harder ones like Diastrac, and which is for acyclical graphs, or like DFS, BFS, which are used very commonly in computer algorithms. We have minimum spanning trees. That's topics that will be covered in, I believe, Usico Gold division. Yeah, sorry. And then, but also that's used in Platinum as well. So Platinum is the highest rank possible in Usico, just for reference. Yeah. I personally have gone through Usico. Well, I personally competed in the Usico, currently Platinum division. Unfortunately, I missed the qualification for IOI, so whatever, that's fine. Yeah, so I have myself never really taken a computer science class. So a few things I'd like to share is where the resources are, and especially LeetCode and Codeforces are great options. There are also books such as Competitive Programming, the Competitor's Handbook, books like these. They are a great source for learning these algorithms, and they gave examples. You're also more than welcome to look at on YouTube or any other platforms for these kind of content. That being said, this is, I guess, the introduction to Python and algorithms. We have reached the end of our time, and if you have any, as per usual, if you have any questions, feel free to stay. If you don't, I wish you have a great rest of your summer, and yeah, thanks all.